So now we're going to break down the combined gas law a little bit and look at three specific gas laws that kind of are a variation of the combined gas law. So what does the combined gas law look like if we kept temperature constant? Okay, so the combined gas law is P1 V1 over T1 is equal to P2 V2 over T2. Now, if we kept temperature constant and we didn't change it, and let's say we're working with the value 1 for each temperature, they can actually go away. And if you keep temperature constant, the combined gas law would then change into P1 V1 is equal to P2 times V2. And this is known as Boyle's law. So now we're going to look at exactly what will happen if we were to change the temperature and pressure or the volume of a gas, how all of these three variables relate to each other. So here we have this mechanism. The black dots are our gas. Let's say if we were going to push this piston down, what would happen is our volume is going to decrease, and if our volume decreases, our pressure will then in turn increase because the gas particles are going to be colliding with each other more, causing an increase of pressure. So what's going to happen is, as the volume decreases, the pressure also decreases. It's important to note that your volume's never going to reach zero because you're always going to still have gas particles. So it's going to create a curve that looks something like this. Okay. So Boyle's law, it's going to relate pressure and volume when your temperature is constant. So whenever you have a pressure and a volume changing, you're going to create an inverse relationship. And your graph's going to look something like this. You can also have V on the y-axis and P on the x-axis, and you still get the same curve. As one increases, the other one is going to be decreasing. Our Boyle's law formula is P1 times V1 is equal to P2 times V2. Okay, so here if we look at this if we look at this picture, on the left, picture A, we have a large volume and very low pressure. But then in picture B, if we decrease that volume, it's going to increase that pressure. All right, so let's practice some Boyle's law problems. A sample of oxygen gas has a volume of 150 milliliters when its pressure is 0.947 atm. What will be the volume at a pressure of 0.987 atm if the temperature remains constant? So the problem, when you see it on the test, is not going to tell you, use Boyle's law. So this is where the variables next to the numbers becomes really helpful so you know which law you have to use. So it says a sample of oxygen gas has a volume of 150 milliliters. That's a V. When its pressure is 0.947 atmospheres. That's a P. What will be the volume, so that's our question mark, when the pressure is 0.987 atmosphere if the temperature remains constant? So our V1 is 150 milliliters with a decimal point for sig figs. Our P1 is 0.947 atm. Our V2 is our question mark, and our P2 is 0.987 atm. So temperature is remaining constant. So I'm going to take that out of the combined gas law and have Boyle's law, which is P1 V1 is equal to P2 V2. Our P1 is 0.947 ATM. Our V1 is 150 milliliters, which is equal to 0.987 atmospheres times our V2, which is what we're looking for. If we do 0.947 times 150, we get 142.05, which is equal to 0.987 times V2 divided by 0.987. Our V2 comes out to be 143.9, but if we sig fig, we have to sig fig based on our smallest number, which is 3 sig figs. So it would come out to be 141, and we want it to be in milliliters because our starting volume was out in milliliters. Hold on, I said that wrong. Your calculator is going to read 143.9. That 0.9 will round that 3 up to a 4, so it's 144 milliliters. That is your final answer. A way to check to see if you did the math right. Here, as pressure increases, your volume would have had to decrease. So if we have these original values of 0.947 times 150, well, our pressure increased to 0.987, our volume's going to have to decrease, and it did. Okay, looking at this problem, a gas has a pressure of 1.26 ATM and occupies a volume of 7.4 liters. So we have a P and we have a V. If the gas is compressed to a volume of 2.93 liters, which is a V, what will be its pressure, assuming temperature is constant? So we're going to use P1, V1 is equal to P2, V2. Our P1 is 1.26 ATM. Our V2 is 7.40 liters. That's our V1. Getting ahead of myself. Our V1 is 7.40 liters. Our V2 is 2.93 liters. So our volume decreased, our pressure at the end should increase. So that's what we're going to be looking for. So we have 1.26 ATM times 7.40 liters is equal to P2 times 2.93 liters. And when you multiply and divide, your P2 comes out to be 3.18 ATM. Did our pressure increase? It did, and that's what should have happened. Okay, so now the next law we're going to look at is Charles's law. Charles's law is when you keep pressure constant. So if you look at the combined gas law, P1 V1 over T1 is equal to P2 V2 over T2. If we keep pressure constant, we can get rid of it in the equation, and Charles's law is going to be V1 divided by T1 is equal to V2 divided by T2. So now the relationship between temperature and volume is a bit different. If we're going to increase the volume, there's going to be more space for the particles to move. They'll have a higher kinetic energy. They'll have a higher temperature. If we decrease the volume, they'll have less space to move. They'll have a lower kinetic energy and thus a lower temperature. Now let's change the temperature. If we were going to increase the temperature and our volume can move freely, those particles will be moving faster, so they would create more volume. But if we slow those particles down by decreasing the temperature, that volume would decrease. So for temperature and pressure, we have a direct relationship. As one increases, the other one also increases. So, Charles's law. So Charles's law specifically relates volume and temperature when pressure is held constant. And as one increases, the other one also increases. So even if our temperature was on the y-axis and our V was on the x-axis, we would get the same conditions. All right, let's look at a practice problem. A sample of neon gas occupies a volume of 752 milliliters at 25 degrees Celsius. What volume of gas will occupy at 50 degrees Celsius if the temperature remains constant? So we have a V, we have a T, we have a T, we're looking for our V. Our V1 is 752 milliliters. Our T1 is 25 plus 273, which is 298 Kelvin. Our V2 is our question mark. And our T2 is 50 degrees plus 273, which is 323 Kelvin. Charles's law states that V1 over T1 is equal to V2 over T2. So here our temperature increased, so our volume should also increase. So we have 752 milliliters over 298 Kelvin is equal to V2 divided by 323 Kelvin. Okay, so if you do 252 divided by 298 times 323, you will get that your volume is equal to 815 milliliters. Did our volume increase? It did, which should have happened. All right, looking at this next problem. A helium balloon has a volume of 2.7 liters, so that's a V, at 20 degrees Celsius, which is a T. The volume of the balloon decreases to 2.46 liters, which is a V, after it's placed outside on a cold day. What is the outside temperature in Kelvin and in degrees Celsius? So here we have to solve for Kelvin and we have to solve for Celsius. An object that is at higher temperature when placed in a colder environment will cool down until it reaches the same environment. It's the transfer of heat. Heat transfers until both objects are at the same temperature. So the outside temperature is also going to be the temperature of the gas in the balloon. So our V1 is 2.75 liters, and our T1 is 20 degrees Celsius plus 273, which is 293 Kelvin. Our V2 is 2.46 liters, and our T2 is our question mark, and we want to solve it in Kelvin and Celsius. So V1 over T1 is equal to V2 over T2. Our V1 is 2.75 liters divided by 293 Kelvin, which is equal to 2.46 liters divided by our T2. So when you do that algebra out, you get T2 is equal to 262 Kelvin. And then to figure out what that would be in Celsius, you subtract 273, and you would get negative 11 degrees Celsius. So we have two answers here. The next gas law we're going to look at is Gay-Lussac's law. All of these names come after the scientists that discovered the relationship either between pressure and volume for Boyle, volume and temperature for Charles, and now we're going to look at pressure and temperature, which was done by Gay-Lussac's. So what is the combined gas law if we keep volume constant? Well, we would take volume out, and we would have P1 T1 is equal to P2 divided by T2. So if we're looking at this, the type of relationship would be, okay, as one increases, the other one would also increase, which would give us a direct relationship. So Gay-Lussac's law relates pressure and temperature when you're holding volume constant. It is a direct relationship. As one increases, the other one also increases. So if we look over here at our picture, if we're going to increase the pressure, the particles are going to be moving faster, so they'll be at a higher temperature. Same thing, vice versa. If we increase the temperature, the particles are moving faster, they're colliding more, so our pressure is also increasing. If we were going to cool it down, our particles are moving less, so there's less pressure. Or if there's less pressure, the particles are moving slower, it's a lower temperature. Okay, so looking at this practice problem, it says a gas has a pressure at 2 atmospheres, which is a P, at 18 degrees Celsius, which is a T. What is the new pressure when the temperature is 62 degrees Celsius, which is a T? So our P1 is 2 atmospheres. Our T1 is 18 plus 273, which is 291 Kelvin. Our P2 is our question mark, and our T2 is 335 Kelvin. Gay-Lussac's law states that P1 divided by T1 is equal to P2 divided by T2. We have 2 atmospheres divided by 291 Kelvin is equal to P2 divided by 335 Kelvin. When you solve this out, you get your P2 is equal to 2.3. We're going to keep that at 2 sig figs because of this value right here.